Morning.
Good morning, ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Sensei, please allow me to speak in bahasa to the audience now. Ya, selamat datang di ITB. Di sini kita juga punya tamu dari UI, Bu Yuni, Prof Yuni dari Kimia UI, dan juga bersama mahasiswanya ada 4 orang. Ya. Terima kasih sudah hadir di ITB. Di sini juga Prof Yuni, kita punya yang hadir di sini ada Dr. Silmi sebelah Prof Yuni. So she's just graduated PhD in our lab, Dr. Silmi. She's from UI, her undergraduate from UI. And then we have master student and PhD student. Ya. Yang Mbak dari mana? Dari Pak Yogi. So we also have a student from chemical engineering. Thank you. Saya mau mengenalkan sedikit Profesor Tatsuya Okubo. Profesor Tatsuya Okubo adalah advisor saya, pembimbing saya ketika saya menjalankan program postdoktoral di Tokyo tahun 2007 hingga 2011. Beliau adalah dosen di Universitas Tokyo, salah satu universitas yang sangat ternama di dunia. Jabatan beliau di Universitas Tokyo berawal dari dekan, terus kemudian wakil rektor, sampai ke sekarang adalah penasehat rektor Universitas Tokyo. Jadi beliau adalah orang yang sangat prominent ya di Jepang. Nah, beliau juga mengabdi juga ke beberapa program seperti Queen Elizabeth Prize for Engineering di Inggris. Jadi beliau mereview proposal-proposal terkait dengan engineering research diundang oleh Royal Family di Inggris. Jadi beliau mungkin rutin datang ke Buckingham Palace ya. Dan mungkin kedepannya programnya menjadi King Charles ya sekarang ya, King Charles. Ya, beliau adalah seorang yang sangat prominent di Jepang dan juga global ya. Profesor Okubo Research Profesor Okubo dengan grupnya seputar material science ya, terutama porous materials seperti zeolite ya. Nanti kita akan dengar paparan beliau terkait dengan sintesis of zeolite dan juga production-nya yang menjadi pengalaman beliau. Beliau juga pernah menjadi council member di International Zeolite Association dan juga presiden Japan Zeolite Association. Ya, mungkin tanpa berlama-lama, so we will invite Professor Okubo to deliver his talk today at ITB. So you're welcome, Sensei. Please.
Organization. I this week here. I really enjoy the very nice stay here. Actually, this is my second visit at ITB, but many times to Indonesia, but to second time. Last time, just like this here, just after he started his position here. So it is a long time since my last visit here. Today I would like to introduce overlap my last 10 years approaches to re-engineering the system production. But I think not all of you are expert of zeolite, so I want to start with some general introduction. Briefly, I'd like to introduce myself first. I got a PhD in Tokyo from chemical engineering. So my generation, I just became 64. My generation, chemical engineering was very traditional, very mathematics oriented, not materials oriented. But fortunately, my research was rather materials chemistry related. So first I had worked on the other material, but I really wanted to work for Zeolite. So after 5 years of professional experience in Kyushu University and the University of Tokyo, I really wanted to change my topics target to Zeolite. Spent 1 year at campaign with Mark Davis. Since 1994, last 30 years, I have worked on focus on Zeolite, especially synthesis and the production. So I had the good opportunity to organize my laboratory as a PI for 25 years. So last year we celebrated our laboratory 25 anniversary. And so last 7 years, I have to spend more time for administration. 3 years as Dean of Engineering. And together with the start of the COVID, I completed my duty as Dean, and I was invited by University President to be the Executive Vice President. I was number 3 position at the University of Tokyo for the last 3 years. So first years, I'm passed to battle with COVID. But the last 2 years, still now I stepped down to Executive Vice President at the end of March. I still take a position as presidential advisor. But my duties, mission is Professor of Chemical System Engineering. As a presidential advisor, still I'm keeping the position of the officer of the green transformation. This is a very important common topic. Sustainability is a very important issue. We pay attention to 3 important topics: carbon neutrality, nature positive, and circular economy. In 3 aspects. So now I'd like to introduce our university's activity for sustainability. Tokyo is one of the first universities to employ sustainability as a mission of the university management. Already in 1994, already 30 years before, in the history of our university, term of sustainability came. Because we started Alliance for Global Sustainability with MIT and ADA. Since then, we put a lot of focus towards sustainability. So very early stages already, we started to reduce CO2 emission on campus, replacing energy-consuming lighting with energy-saving lighting, energy-consuming air cooling system, refrigerators, we are energy effective systems. We did this approach for last 30 years. Based on this background, current President Fuji started Tema in 2021. At that time, he invited me to the Executive Vice President. And in October 2021, we decided to participate in the Race to Zero campaign, which is organized by the United Nations. This campaign is, by joining this campaign, we declared to be a greenhouse emission-free university by 2050. So now, as I'm the carbon neutrality throughout this campaign, as an officer, I'm mission, very heavy mission, to realize planning of the carbon neutrality of the University of Tokyo. First, we analyze emission source of CO2 from our university campus. Our university is a very big university, and also research university, and the many big research facility of the science, engineering, medicine, and so on. So we are using a very lot of the electricity, and we don't have a power generation system, so we have to purchase electricity from outside. But unfortunately, in Tokyo, green electricity is not enough. So we have to believe our CO2 emission must be due to electricity consumption but it was not true. We are very good research people on the life cycle assessment. Have you ever heard the life cycle assessment?
LCA.
LCA. It's a part of chemical, especially very close with chemical engineering, especially process system engineering. For example, in order to make this PET bottle, CO2 is emitted. In order to as a waste treatment, CO2 is necessary. Total consumption have to be considered. This is life cycle assessment. Mass balance, energy balance, all based on the chemical engineering background. So with considering all factors, our CO2 emission by electricity is scope 2. Scope 1 is direct emission, but we don't have power generation. Also, we don't use heating by combustion. Mostly we are using electricity. So a heat pump. So, but this part is only this is the energy related to the fuel, transportation, and so on. This blue plus orange is the total emission by electricity, but only 1/3. What is the others? All indirect emissions. We purchase several chemicals, we purchase several goods, also we construct some building, also we remodel building. Such an energy, indirect energy consumption, very huge. It is very clear that university cannot be carbon neutral by themselves. Common for every university. Society has to be green enough. So this is a very important mission worldwide university, because university does not produce any, for example, chemical product. We produce people. We produce people for future. But we don't produce energy, we don't produce product. So our important contribution is to work together to carbon neutral together with society. This is a very important message we could understand. What is interesting? Compared with other universities, not so many universities to disclose scope 3 indirect, but because very difficult to calculate. We are calculated based on some assumption. We have to precise much more for the future. But anyhow, this is our outline. But what was interesting compared with our universities, US university or Australian university, emission by commute is very low, because Tokyo, we are located in Tokyo. Tokyo is a very nice public transportation, and the space for parking is very limited. Because of this, we have a limited consumption by the emission by transportation. And the business, also business travel. We have many business travel we can do by train. Now you can make a train here. But for example, in the case of US or Australia, they have to use airplane for travel. And the commuting, they have to use automobile. So there are different approaches. We cannot say from this part. So also what is important? Our university has a big land, big forest. Our university has 7 forests. 7 forests. So 2/3 of Japan land area is forest, very rich in forest, but mountain forest, same as Malaysia. And our university owns 0.1% of this forest. We are a big owner of forest. And this forest absorbs almost 70% of our emitted. So maintenance of the forest is worldwide very important. Of course, not only forest. You might know blue carbon fixed by ocean area. You have a very nice ocean area. And so maintenance, the management of nature is also very important issue. Previously, our university forest belonged to School of Agriculture, but now by combination with engineering agriculture, we are going for the next step. Of course, already wood was used for materials, so wooden structure keeps CO2. This is carbon neutral. CO2 is fixed as a structure. So wooden structure is very useful. Also to the country, earthquake, which is earthquake, but some design of wooden product is very strong toward the vibrations. And also wood was used for fuel. So this is a carbon neutral fuel because this the process of the grown up of the plant. CO2 is by photosynthesis, fixed by photosynthesis. And now here comes the third important role of this forest. That is the carbon source, biomass. This is also renewable carbon source. What is used for this carbon source in the present chemical industry? That's oil. But the oil is not renewable. It takes 1,000 years to make oil from. So it is very important timing for us to tackle together. Now, biggest forest owner in Japan is Hokkaido University. Hokkaido University is the fourth owner. Our university is sixth owner. The other companies. We are now making some forest lead to make the changing some industry for the future. So I will go to the topics on zeolite. So zeolite is very much relation with this chemical conversion and storage and separation. Zeolite is crystalline inorganic porous materials, mainly containing silicon and aluminum by breathing oxygen. So this element is very high Crux number. Crux number is the element containing the earth. So very affinity is very high with environment. And because of the flexibility of bonding angle, more than 200 kinds of the structure have been recognized. So very large surface area, sometimes 1 gram of powder shows the surface area of 1/10 square. So far, zeolite is very much applied in the industrially and also in our daily life. Here, do you use liquid detergent or powder detergent, which is common here?
Powder detergent.
Powder detergent. So inside the powder detergent, 10 to 50% is zeolite. Because in order to soft water soap work very effectively, but hard water does not work so much. So hard water is due to the minerals, magnesium and calcium. This is exchanged with sodium. This is the reason why zeolite is added to salt. Also, in order to make gasoline, zeolite is essential because crude oil contains many different types of the organic molecules. But the effective molecules, gasoline is around C8, C7, C8. Diesel oil is a little bigger, but it's C10 to 12. So heavy molecules have to cut. In order to cut molecule, acid is very effective. Acid catalyst. Previously, liquid acid was used, but the liquid acid often brings some environmental problem emitted to the environment. So solid acid is employed. Finally, zeolite is used for this production. Huge amount of zeolite is used, but unfortunately consumed. In order to make a pet bottle, what is the most important xylene for this polymerization? You know three xylene, automata para. Which is the most important? Only para. Para. Because para can easily make a chain. But generally, these chemicals separated by distillations. So distillation is a very basic first separation technique for chemistry, chemical engineering students learn for the first time because it is very easy to design. But the case of the para and parameta, para 3-xylene, boiling point is too close. Energy efficiency is very bad. So worldwide, this separation is done by zeolite. Slight difference is division rate, automata para division rate. So worldwide, this separation is done by zeolite using simulated moving bed reactor. Continuous operation of chromatography. Chromatography is very effective, useful, but not very good for mass production. So simulated moving bed is very special reactor system invented by UOP company. So these are very big growth in the history of their petrochemistry, 60s to 70s. In addition to this traditional usage, here comes a very important application. We had a very big disaster of the Fukushima nuclear power system after a big earthquake. Unfortunately, several element was emitted, radioactive element was emitted. We have to recover these species. One of the most difficult issues was cesium. You know cesium. So sodium.
Yeah. First group.
One of the
First group.
Yeah.
Elements.
element of table. Helium.
First group, yeah.
Alkali. So this ion exchange was very useful. So first, special title silicate was used, developed by San Diego National Laboratory, US, and the UOP company. But later on, much simple zeolite was very used. That's the history in Japan. So now, zeolite is essential to clean up radioactive species. Also, gas treatment of car. So for gas engine, gasoline engine, three-way catalyst is a golden catalyst to reduce NOx to N2. But the case of diesel truck is comprehensively diesel is used. Big seat, diesel engine. Now, agriculture machine, diesel engine. Because diesel engine has power. But the diesel engine emission is low temperature, more oxygen. Unfortunately, three-way catalyst does not work. Also, three-way catalyst, most significant disadvantage of three-way catalyst is the precious metal, platinum, palladium. These elements have to be introduced. Alternatively, in the diesel gas treatment, now zeolite, copper, chabazite. This is invented by Engelhardt, now part of BSA. It is used copper. Also, sometimes iron. These elements is used, but they have to use reductant. Can you guess what is the reductant to use? Of course, if we can use hydrocarbon
unbound hydrocarbon, it is the best story. But unfortunately, not the case. We have to add another reductant. Already in the power generation, combustion system, if you use oxygen, if you use air or oxygen, NOx is formed by oxidation of N2. So what is used for this reductant for the power generation system? Not the hydrogen, because hydrogen reacts more with air, oxygen. Not CO. CO is also toxic. Answer is ammonia. Ammonia is injected in the power generation system, big power generation. But the automobile, impossible to carry ammonia in the gas. So urea is used. Solution of aqueous solution of urea is used. And the aqueous solution of urea is injected into the diesel engine. So for this application, zeolite is used. Also, antivirus materials as zeolite, silver zeolite is very effective. Silver zeolite is often used. In Japan, it is very popular for the cleanup of the bathroom and some toiletries and some teeth brush and so on. Also, our group work with painting company. So this zeolite also used to cover the COVID. Acidic zeolite is very useful for the battle with COVID. In addition, so now, do you know how to make oxygen, nitrogen industrially? PSA. PSA. But the, in the mass production, how do you make pure oxygen, pure nitrogen? Not distillation. So emit to cool down and then liquefy air. Then distillation. This is the industrially used process to make air as oxygen and the nitrogen. But the smaller scale, PSA, pressure thing adsorption is used. Adsorption. So for these applications, especially zeolite, lithium exchange photosite, lithium LSX. LSX leads to silica ions. So aluminum rich X-type zeolite. So this is very, in Japan, this is very common in the factory and also hospital to make pure water. But during COVID, oxygen is very important for medical care. So very compact type power generator is very useful for many hospitals to take care of the COVID. Because COVID people damage lung. So oxygen, this technology saved many lives in Japan. For the other country, often gas cylinder have to be used to provide pure oxygen. But locally, by this small scale PSA system, this was very useful for the during COVID. So, as I talked to you, zeolite is very many useful materials. Also for future, for the era of sustainability, as I already told to you, we have to make a new chemical process based on biomass. Also, we have to change some energy efficiency very much because chemical industry produce a lot of energy, especially separation. Lots of energy worked by separation. Many things to do for separation. So, even comes the era of the sustainability, So green transformation towards carbon neutrality as well as nature positive and circular economy is very important. Zeolite so far play as catalysts, absorbent, ion exchangers, and also used for automotive, medical uses, nuclear technologies. So still game-changing innovation. Zeolite should play a very important role in reaction, separation, storage, and so on. So this is big motivations. Now here comes a very interesting approach of Zeolite for the startup. One of the targets is DAC, direct air capture. CO2 level here is 400 ppm. So chemical engineering learn fast. If you want to concentrate, don't dilute fast. Because required delta G is related to the log of the concentration ratio. So if it is diluted, more energy for concentration. So in this sense, 400 ppm is not a worth target to concentrate. So far, people never pay attention, but right now, really carbon negative technology is necessary. So now people pay attention to several methods for the recovery of CO2. Among these approaches, my good friend, Mark Davis, found out, he's my boss at Caltech. He found out one type of zeolite very effective to concentrate CO2. That is molten. Actually, he found this fact and submitted the paper to proceedings of National Academy of Science. PNS assigned reviewer. He assigned to reviewer me and the Chris Jones. Chris Jones is the former student of Mark Davis. He's the expert of that. There's a one big company, Global Thermostat, is from his invention, based on his invention, not zeolite. Porous, modified materials. Roger worked for this project, he was there. Yeah. But he has never worked on zeolite, but now he decided to start with math. They started a new company, Zeolite, based on Caltech pattern. Also, one of my colleagues, Kenta Yuki, he was my group member till March, but now he is independent here in the other campus of our university. Separately, completely separately from Mark Davis, he started his own company for product sales. So, of course, CO2 recovery is a very important mission, but some area, water is very much important strategy, especially in Africa. Maybe much better in this area, lot of the rainfall, but the Africa was some Midwest. Yeah. Water is a very strategic material. So in such an area, not only CO2 recovery, but also water provide is also very important. But the energy management is the key issue for this technology. So my motivation of re-engineering, too long introduction, but here comes the objective, my goal. In view of the materials and the energy aspect, zeolite synthesis and the production, are they rational enough? Such a good materials, but can we make these materials effectively? Or our processes environmentally benign enough? That's my motivation, my goal. Zeolite synthesis, briefly, I'd like to introduce. Zeolite synthesis is done in the very strongly based hydrothermal condition. And in the alkali, water is reaction medium. And in very basic conditions, silicon and aluminum source is added. Sometimes organics is added. And organic act as some structure direction. Sometimes, previously it was called template, but the relation of the organic and the polar structure is not one-to-one. recently it is so-called structure directing, organic structure directing agent. But this process is very complicated. All is done in the black box, in the reactor system. It is a pressurized reactor, so body is very hard. And it is, I will compare with zeolite synthesis with cooking here. And the zeolite first synthesis was done in almost 100 years before, during World War II. First synthesis was done, learning from natural zeolite, formation of natural zeolite. There are two types of zeolite, natural zeolite and synthetic zeolite. First synthesis zeolite was done in 1940s, and the mimicking some natural zeolite. Several zeolite was found. There are several very important natural zeolites in Indonesia. And also in Japan, there are very high quality modernite, natural modernite. So this natural modernite work for the recovery of system. And later on in 1960s, new organics was used, zeolites. And the new type of zeolite has been found. In these days, very important zeolite for the acidic catalyst and the several separation catalysis was already found. Then in 70s to 80s, energy crisis had happened. In these days, still very important zeolite so far, DSM-5 was found. High silica, strong acidic zeolite. Later on, 90s, science of zeolite synthesis was very much big progress thanks to Mark Davis, Stacy Don Chevron, also Abelino Colma of Valencia. Very important contribution made. But unfortunately, synthesis became too complicated, too complex. So although many papers come to Science and Nature, but these were just for reporting to the publication. So now Nobel structure by more complex synthesis. So still we have more than 250 zeolite reported so far. Still around 10 zeolite being used for the commercially because synthesis costs too much. And the very difficult component is used for this application. Still so much to do. So I already told to you that zeolite looks like some similar to cooking. Autoclave is exclusively employed for hydrosample synthesis. Same for rice cooking. You need a rice cooker. Very similar. Autoclave is very similar to rice cooker. So, and the batch operation, chemical engineer run mass production, continuous flow reactor is useful. There are two types of continuous flow reactor, plug flow reactor, and the continuous start tank reactor. Two types of chemical reaction engineering taught the student, two types of continuous operation. But so far, only batch operation. And the synthesis performed at once, not step by step. Organic synthesis, imagine organic synthesis. First reaction, separation. Second reaction, separation. Each reaction condition, different temperature, you can choose. But the autoclave, impossible. Rice cooking, same as rice cooking. Put everything together, sometimes coconut milk, sometimes saffron. I like coconut rice. Today, unfortunately, saffron life.
Nasi uduk.
Then close, just a plate, that's cooking. Same as zeolite synthesis said. And the people believe zeolite synthesis is a very slow process. Hours to day, sometimes a week. People believe zeolite synthesis is very slow, reaction is very slow. This is the common sense. Complicated issue of selection of static material, same as cooking. Also, adding order is important. This is very unique. Chemicals A, B, C, adding order is very important. If changes, different materials produced. sometimes organics are essential for the synthesis. And the recycling use of organics, because cost of the organics is most of the starting materials. Of course, reuse is most important, but in the most cases, reuse is impossible. Cost very expensive to recycle. And so how do we treat these organics? Just burn out. In order to remove in order to make porous space, have to remove organics. Just burn. So aging and the photosynthesis treatment are employed. So aging. So same as cooking. Before start cooking, keep in the room temperature for a while is very important. Especially for the site. Why zeolite synthesis? This is the essential part. Very similar to cooking. But the higher barrier for this is the state of the art of understanding. So this is a very high barrier for the outsider to zeolite synthesis. Compared with more or with porous materials. So we are very lucky. So because the player number is so much limited. Some of the examples. If we change the adding of the different materials, in order to obtain for the LCC catalyst, aging is essential. So when making, mixing is very important to make a homogeneous condition, but the mixing is very disadvantageous for FCC production. Have to be static. So how to rationalize this? For example, cooking. Adding order of the items is very important. So-called sashisuze in Japanese. Adding order sugar, salt, vinegar, soy sauce, sashisuze. In order to make a good dish. It is very similar to this cooking. But we should understand this in terms of chemistry. This is my starting point. Already, there is a very good report on the understanding some chemistry of porous materials. But you can see energy difference of several materials is not very big. Zeolite is located in very small area. How should we understand this state? Before zeolite, I had worked on several different materials. So what is important to understand what control the product, synthesis product? My answer is kinetics. Because energy difference of the several porous materials is very small. This difference does not determine the synthesis product. We have to understand energy landscape, also reaction pathway, reaction paths. So if product is controlled by the equilibrium, independent of the root, we could get the thermodynamically stable product, depending on the reaction group. But this is not the case for zeolite. Adding order is very important. Several procedure, aging step or something is very important, showing that selecting the reaction rate is very important. We have to understand reaction scheme of zeolite, not by Mount Fuji, but by such a complex mountains. It is like some golf to have a suitable point by selecting the suitable hiking route. In order to go to the suitable place in the mountain area here, we have to select suitable route. But we cannot arrive at the target places. Reno invited me to go to volcano. But in order to go to volcano, we have to select suitable route. The synthesis is the same. Based on this understanding, all of the phenomena could be understood. What's important is how to describe this in terms of chemistry. So, with these approaches, we could synthesize zeolite. So far, people believe organics essential to achieve. But the beta is industrially very important zeolite. But the people have to believe organics is essential to make this zeolite. But the key issues, we demonstrated nucleation, organics is essential. But the crystal growth, we demonstrated if we can add the seeding, crystal growth can be done without organics. With these approaches, we succeeded to make zeolite effectively without organics. Now, this is deployed in the standard synthesis textbook, and also based on our patent, we made a startup company already 12 years before. Very big reactor, 2 cubic meter reactor, 3 cubic meter reactor, and the mass production. Now we started company, University Zeolite, Uniseo. Unfortunately, this company already gone, but the old patent and the manufacturing is Mitsui Metal Smelting companies. Big producer of the automobile, bicycle catalyst, motorcycle catalyst, but they are interested in automobile application. So also, my important contribution so far is aging. Aging is just operation. People regard aging as operation, not the heat up. Just leave at the room temperature, then heat up. It is so-called aging. But we demonstrated aging is really chemical reactions. So from the NMR, we can see during aging, reaction of silicate and aluminate proceeding. So very easy images this. There is a 2 types of pink color. Pink color is the mixture of the white and the deep pink and the homogeneous pink. Because aluminate in the alkali condition, once aluminum is dissolved in the alkali medium, very easily react with surrounding silicate. So in the initial stages, if assume aluminum is lead, deep lead particle is first formed. But if hydrothermal reaction started here, high aluminum zeolite, like LTA zeolite, or sodalite is easily formed. We have to wait all the species to be homogeneous. This is the meaning of aging for photosynthesis. So this is one of the examples. This is the first work we did with Professor Ogura. And so we did this type of the several basic study to understand the formation scheme of zeolite. Last 10 years, based on our understanding of zeolite formation, we have tackled on several topics. But today, time is limited. We can do some of our recent topics. Maybe time is so I will skip maybe 2 topics today. First, now it's a day of the information data. So zeolite synthesis, huge amount of data is stored, but not very organized. There's a recipe book. I joined Caltech in 1993. I wanted to start zeolite synthesis from zero. I want to go to the, I believe that Caltech is the best place, but what's the importance of the recipe book? There's 100 pages of recipe book. In order to make a zeolite, every time recipe book, everybody read recipe book. Then based on this modifiers, try and error was essential. But in order for the future, we should rationalize. This is just one example of zeolite. Data, information. This is very useful. Unfortunately, I'm too old to work on these topics, but we are very lucky to have a very young talent to work together. So first, our success was done with some data approach, machine learning. So my student checks more than 600 literature. And very important key person is Ruang. He is now assistant professor, tenure track assistant professor in our group. Not my group, no anymore. He is my student. Sada undergrad student. The bachelor, we don't know very well. He is now National Institute. He was a research assistant professor at the time. Bachelor supervised all students. I was so surprised. They collect 600 data, machine learning. This is Zeolite systems without organ, traditional Zeolite systems. Just by machine learning, they rationalize knowledge of Zeolite synthesis and trees. But this tree clearly demonstrated, classified very important part of the SDA-free Zeolite synthesis. We have worked on this synthesis very much, and also we had the retired person from industry, Dr. Itabashi. He's the expert also Zeolite. He also agreed with this. We are all surprised. So machine learning is first we realized that this is very powerful. Now, already we did in the 5 years before. Then, also, he tried to rationalize synthesis with organics, and we could find out new SDA to make new Zeolite systems. So not only for the SDA-free Zeolite, but also the seeking of the organics is also very useful. Not necessary to make trial and error. Of course, recently, theoretical approach is possible. Computational theoretical approach, data approach, and experimental approach. We can reduce trial and error time by employing this data approaches. And recently, ant-colony optimization scheme is also employed for this design organics. So I'm not very good at chemistry, but by using this approach, we could find out reasonable organics for the Denox catalyst. So not only our group, but also MIT, Valencia, team worked on this similar topics. And Raj and I write a perspective to general science, and to other topics, MIT, Valencia, joint work. Schwartz Koda is a graduate student at the time. He's Brazilian, Japanese Brazilian student. I met him in one conference. And they clearly demonstrated a protocol to design organics towards demanding Zeolite structures. Now, we are more paying attention to several approaches to Zeolite. Okubo is now, he's now for a year after his PhD, now he's a senior assistant professor. He's independent, but we are working together in the futures. Now, recently, AI, ChatGPT, AI, this is not our work, but his work. Using ChatGPT, he claims that ChatGPT is also very useful to identify necessary SDA. Now, this is under review in the Nature Materials paper right now. Hoping this will come out already in the Tema archive. If we are interested in Tema archive. Now, not necessary, sometimes not necessary to do everything by theoretical. Such AI approaches already, we can use this scheme for the finding out Zeolite. This is one of my message. So not only theoretical, but also data approach is very useful for our future, especially young generation. Please pay attention to the next ultra-fast synthesis. Zeolite synthesis, people believe, hour to days or week are common. But my question is it true? So in order to make hot water, kettle is very useful. But in order to make some bath, shower, do you use kettle? Scale up is not effective because area is just square. So we have to use continuous operation, not batch operation, heat exchanger. This is a common sense. Very easy to understand. Rice cooking. Japanese zojushi, very but this is the industrial scale. Quite different design. This is a common sense, but as an example, but this is the industrial aspect, but the paella, Spanish Valencia, but this is the art. This is the example, but this is art, not culture, but not the industry. But the industrial aspect, this is not the straightforward way, but there are syntheses like paella. There are syntheses like paella. So this is my question. Is the final answer? My answer is no. So I'm a chemical engineer. So I examine the process of chemical engineering, the production, conditioning of the mixing, aging, heating, cooling, and so on. We pay attention to all operations. They are connected in series. If these processes are connected in series, overall rate is controlled by the slowest step. If escalator and stair are connected in series, so slowest step, stair control all of the rate. If escalator and the stair are parallel, fast process, elevator, escalator controls all the rate. So this step are connected in series, slowest step controls everything. So formation of aluminum silicate, fast mixing. This process itself is a fast process. But the conversion of aluminum, just of aluminum silicate species, deep red to the pink, this step is slow compared with this mixing. Nucleation should be slow. Crystal growth, people have to believe slow. But later I will show you, this is not slow. Slow step is the others. So, by understanding each step, we demonstrate it to show zeolite in minutes, sometimes seconds. I will show you the example. Oh. So first, we have to think about so why these are connected heating. So we have to make each step faster, faster, faster. So, first, what's important? Autoclave is comprehensively employed for the synthesis. Autoclave is very slow to heat up. In the stainless steel autoclave, it takes 1 hour to heat up over 100 degrees C. But sometimes aging step, unwanted reaction proceeds in the heating step. So each heating step has to be minimized. That was very important motivation. We could do this, and then we demonstrate how cooking. It is like some approaches. So as I already told you, paella is art of cooking. But previously I used some picture of fried rice, but today it's in Indonesia. I use nasi goreng. This is a systems approach because in the case of paella, one pan, boil up soup, stir fry, add rice, add meat, then bake. But in case of the nasi goreng, fry meat and shrimp, take out, fry some veggie, then finally mix together. So very systematic approach. So we need some such a systematic approaches for zeolite synthesis. So in order to minimize some reaction time, aging step should be optimized. Conversion of the just mixture or unsophisticated into the precursors. If temperature is high enough, unwanted nucleation start, but the heating up, but not too much. But the aging at the room temperature is slower than the aging at, for example, 50 degrees C or 60 degrees C. So we employ without autoclave, aging at the longer time, but not the time for nucleation. And the seeding, often we use the seeding, skip nucleation. And also reaction at a higher temperature. In the case of the synthesis with organics, often maximum temperature is around 200 degrees C because organics decomposed. Also, reactor, often Teflon is employed. Teflon does not accept higher temperature. But we realized if reaction crystallization is high enough, we can complete zeolite synthesis before the decomposition of organic. Also, if aging is good enough, organic is stabilized by inorganic part. So, in order to, traditional crystallization consists of two steps, nucleation and crystallization. But the case of zeolite synthesis is really different, aging. Conversion of starting materials is very important. So we have to optimize each step, as I already told you, chemistry of aging. So we try a system approach, longer aging, seeding, high temperature environment with faster heating. So enable total system in the minutes order. We call ultra fast system. So in order to realize this mixing step, aging step, crystal growth step, have to be separated. In order to realize temperature response have to be high enough. So we skip to use conventional autoclave. We make very simple reactor, very cheap, simple reactor. Stainless tube with straight rope, that's all. So first we try to use oven for heating up, but very slow. So we just employ fried chicken, cooking, tempura, heated oil, just throwing. Less than minutes, very fast heat. So first we fry alcohol, just 1 minute. Case of the SSS13, so 5 to 10 minutes. Conventionally, it takes hours or days, but we could demonstrate such a synthesis can be done in very short time. So also from this shape, you can see we can apply this to the plant flow reactor, continuous flow production, very high productivity, guaranteed. So we could demonstrate this synthesis. And also in the extreme condition, near supercritical condition, we could demonstrate GSM5 to be made in the second order. This is an extreme example, but this case the temperature is too high now. But it's demonstrated that it's possible. So for the several zeolite minutes order reaction was demonstrated. So really we could employ higher temperature than usual. So it is good enough before the decomposition of organics. Zeolite crystallization is complete. So my co-worker, Dr. Ulrich Müller, he's a retired BASF, research director of BASF. He retired a few years ago. He came to Osaka JLPC meeting. We had a very good talk with him. At that time, he made this slide for us. He gave us academic, 1 day, 1 cubic meter, 1 to 10 kilogram productivity. This is academic. Industrial batch reactor system. 1 day, 1 cubic meter, 100 to 200 kilogram is a batch operation. But he calculated based on our recipe, almost 3 tons per cubic meter per day possible. You can see compared with traditional academic, industrial, more than 10 times. Very highly energy saving production can be realized. This is one of the example of re-engineering I want to introduce today. So also, this approach is very useful. Mesoporous materials, mesopore is very useful for catalysis for the transport enhancement. Mesoporous zeolite, very famous mesoporous zeolite was invented by Professor Javier Garcia Martinez. He was a former president of Ireland. And he is a good friend of mine, and we work together. His method for making mesoporous zeolite, we could demonstrate this formation in minutes or enough to make some mesoporous zeolite. Also, encapsulation, ultra fast encapsulation. Sometimes encapsulation of the metal nanoparticle inside zeolite is very useful. But often, zeolite synthesis is slower than the particle formation. In situ formation is very difficult to achieve. But in our cases, zeolite crystallization is fast enough. So we can make in situ formation by using this our reactor systems. So we could demonstrate similar encapsulation of the metals in the course of zeolite crystallization. This is published in Lantai. Also, we could show several catalytic performance of these synthesized materials. So time is limited, so I will skip this part. And now we can monitor zeolite formation in situ by using some high energy X-ray scattering method. But the time is already I talked too much, so I will skip. So if you are interested, I will introduce these topics later on this afternoon. So now, by using some synchrotron radiation system, spring end, we could in situ monitoring the zeolite formation is realized. At last, we achieved after 20 years trial and error approaches. So I'd like to summarize my talk today. So my conclusion. So far, zeolite synthesis is like hydrogen, scale up. But the alternatively, as I already told to you, I don't think this is not the final answer. Still, we have so many things to do. That's the engineer. So far, forecasting based on present, forecasting is very important for engineering. But it is error of sustainability. We have to realize carbon neutral society by 2050. So we need another approach is backcasting. Let's realize future by backcasting our desire. Okay, it's very important mission for science and engineering. So this is my message from engineering of zeolite synthesis to re-engineering of zeolite synthesis. So I'd like to introduce many of my collaborators for last 10 years. And now already Wakihara Ioki Muraoka is independent position in the University of Tokyo. So I will retire in a year and a half, but unfortunately, there are several zeolite people who work in Tokyo. And also, Zenon Liu, who has worked on neutral path synthesis, he is a senior professor in Beijing, Chiba University. And this is the current member of our group, Professor Sano, Professor Emeritus Hiroshima University, is worked for us. And also, Rakeli is from Valencia, Heidon from Shanghai, Takemoto from Osaka. These are current members. I'd like to also acknowledgement to the co-workers. So this is the current member. So sorry for my long talk today. I mean, this is a really final slide. So thank you very much for your instance.
Thank you, Okubo Sensei.
Too long talk, sorry.
No, thank you, Okubo Sensei. I think we enjoy your talk, so we want more actually. It's still short, in our opinion. Yeah, so in our university about the carbon neutral. So we, of course, we have not done any maybe sustainability report for that issue, but in our university, we at least we apply that we cannot also use a plastic PET bottle in the for the meeting. But I'm sorry, except except this one. So PET bottle.
Also, I introduced some water server to the campus.
Yeah, PET bottle is not allowed. So normally we provide this kind of glass.
Yeah, we are doing the same approach.
Yeah, but today our student actually enjoy the milk with not the plastic but with some paper. Paper. Yeah. So the forum open for questions. So I'm sure there are a lot of questions from the students and participants. Please, maybe Prof. Uni first. Yeah, please, Prof. Uni. So use the mic. So
I
we
think
can.
my voice.
Yeah, it's okay. It's okay.
Okay, it's always very fascinating and interesting talk from you from time to time. I always find that it is always like new things that I always learn from what your talk, and I'm sure that the students also feel the same. Okay. My question for the actually is it is interesting to have a very ultra fast synthesis, you said, because it saves time and also it's, but then I have two questions about that. Yeah. It seems that for zeolite synthesis, the process is already from aging and until the crystallization. I just wonder if those steps actually there's some that skip or actually they happen also, but extra fast, ultra fast. And then the second one is when we want to upscale, you said that it is not as easy as just enlarge the volume and etc. What that we need to modify or adjust, yeah, if we want to use this ultra fast.
So first point, for example, nasi goreng.
Nasi goreng.
Sometimes already cooked nasi goreng is used for the next week. Yeah, so this is a good hint for us. So we can modify synthesis. Traditionally, we just learning some basic, but this is controlled by the common sense. But the outsider, actually speaking, we could realize that ultra fast synthesis by joining Zendon Liu. He had worked on continuous microreactor of the polymer in master degree in Jepang University, then joining our group, first person of zeolite. He has no common sense for zeolite synthesis. So he made some reactor by stainless steel and it's very good. Yeah, such a now we are controlled by too many common senses. We should go back to the principle. Principle, when I joined chemical engineering student, I learned thermodynamics told us where we can go. Then kinetics told us how long does it take. This is the essence. That's all. So rate, also I learned rate is not only reaction rate, mass transport, thermal transport. These rate processes are very important. I learned this. This is basic. I'm not chemistry background, chemical engineering background. Maybe this is, I could contribute different contribution to zeolite synthesis because so far zeolite synthesis was done by chemists. But the chemistry, common sense. Of course, common sense is very important for safety issues. But sometimes, this is a good example, outsider. I'm also outsider. I had worked on CBD and so on, then come to here. So seeding was very common for CBD. Also, cold synthesis seeding is very common. But the zeolite community seeding was unusual. But membrane, now membrane, we are the first to make zeolite membrane by seeding with life supporters. But now seeding zeolite very common. So sometimes broad the boundary is very important. The second question. So BSF and I, also Mitsubishi Chemical and I, we try to make zeolite samples. Because zeolite, several different batch formation is very important. Very fast process, very energy saving. That's the point. For the future, recycling is a target. Recycling to reduce waste. That's our future target.
Yeah. So it's also we have to think out of the box, isn't it? So yeah, in order to create innovation. I want to ask Sensei actually show the ZSA5 synthesis in an ultra fast way, but it's a continuous flow.
Yeah.
But how about the batch reaction?
This
Can
is
you still get can you still get the fast result?
so we have a similar recipe, and in the shortest time, few tens minutes was possible in the very high temperature.
I think it's like number 50 something.
Okay, and all depending on the environmental conditions. But sometimes too high pressure reactor cost expensive. So pressurized reactor, hard instrument necessary. But also operation is very high pressure, getting high pressure. All depending on the total cost estimation and safety.
This is not considered high pressure.
This is very high pressure because 370 degrees, supercritical temperature. In such a cases, special metal sometimes have to use. So the pressurized pumping system is very special pumping. So all depending on the design. Still design flexibility. All depending on the target. Also DSM-5, many different grades of DSM-5. Highly silicious DSM-5, also titanium DSM-5, TS1, depending on target. Today I skipped my topics. But by selecting suitable starting materials, we can design this.
Batch reaction is possible.
But of course,
Yeah, for ZSA5. Okay. So please ask. Yeah. You have to use microphone because recorded in the voice not cannot hear. Yeah, please. Maybe yeah.
My name is Prof. from University of Indonesia. Thank you for your amazing presentation. I have experience. There are a lot of aha moment for me because there are a lot of factors that can affect the structure. My question is, I saw that there is an application for Zeolite. There is a sort of CS as radioactive element.
Cesium.
Yes, so ion exchange. It was interesting because I also use faujasid, if I am not mistaken, because the structure is like faujasid. Because in my last project I used white zeolite. I'm just curious, how do we improve selectivity for cesium absorption? Do you have any suggestion, maybe to set the font size, or it is selective just for cesium? And how we set the zeolite not absorb the element that has similar size with cesium or lower?
okay. So in the case of cesium, separation surrounding a lot of sodium. But the key was how to correct cesium. So in the Sandia UOP developed special porous materials, titanium silicate. So titanium is octahedral, silicate is tetrahedral. So they employ very special materials by design. Surely, based on the structure, it is very advantageous cesium. But the natural zeolite bar, people never imagine. Because natural zeolite is not very specific, but it works. Sorry, but I don't understand why it works. Maybe kinetics, but sorry, I have no clear answer. But in the case of natural zeolite, different from zeolite is that they contain alkaline earth. I don't know what really answer why, but it is true. Natural zeolite is yeah. And the cesium is of course bigger, but the alkaline metal. And the also cesium is this is radio isotope cesium is a target, not the conventional cesium. But it was this is a total story. As far as I know, not specific recovery of the isotope, but the total cesium is selectively recovered. But this is all information I have right now.
So, any more questions from the students? Please, yes.
Thank you. Sensei, my name is Naoki Madani. So, in our laboratory, one of the research is about CO2 absorption. And I choose a cellulose carbon nanotube instead of zeolite.
Yeah.
Because the reason is about the sensitivity to moisture.
Exactly. This is a key point.
Yeah. Other than CFD, I also plan to use zeolite, but the issue of moisturizing, I want to find out how to address this issue.
Yeah. Very, very important point. This is a comment I comment to the reviewing paper. So zeolite is very high affinity to water. Also, sometimes very difficult to remove water. So how once water is kept, zeolite power is not effective to recover CO2. How to battle on this? This is the essential part. The solution by Mark Davis pattern is to use MAPO. Not alpo, but MAPO, metal phosphate, porous metal phosphate. Not conventionally to remove water, A-type zeolite is used. But the A-type zeolite is too strong affinity to water. Once kept, no release. But regeneration needs a huge energy. But they employ metal phosphate made by Mitsubishi Chemical for the use. It is easily trapped water, two stages of the adsorption. First stage is water removal. Then second stage for CO2 separation. So totally they investigated energy analysis. It works. So they claim water can be provided from the system. Also, I did not tell you the detail of the molybdenite. Molybdenite cases, when physisorption occurs, exothermic heating, temperature increases the essential problem for absorption because temperature increase, reduce amount of absorption. But surprisingly, in the case of molybdenite, CO2 trapped, but less heat emission. Maybe entropic condition in the absorbed CO2 is higher. Maybe side pocket trap CO2. The completely separately with their work, we have one paper in chemical communication on the N2O effectively trapped in natural molybdenite. N2O, CO2, both very high greenhouse gas. Structure is very similar, linear molecule. Size is very similar. We are assuming both molecules can trap at the side pocket with a high entropy. Maybe rotation is allowed in the trapped condition. This is a new design of absorbent. reducing the heat emission by absorption is very important part of this new design. So, sorry.
Any questions? Please ask more.
So the solution is to process the feed before the thing. And another solution maybe is there good option of zeolites, for example, in the presentation before the zeolite for absorbing, for example, by zeolite on the night, data. So in your opinion, which zeolite is the best to address the moisture?
Moisture issue. So far, judging from the paper, maybe this MAPO is very useful because this material is developed by Mitsubishi Chemical for the air conditioning system. They want to use the air conditioning system by absorption. Absorption, desorption is very huge heat is emitted and absorbed. They employ this air conditioning system, but the business was not very successful. But they made this special one. The kinetics is very important in case of the heat management.
Yeah, so there are students actually work in the synthesis of zeolite. So maybe you want to ask question. Rita, maybe? Yeah. Oh, okay. Oh, Dr. Grand Prix coming. Okay. So he just got a award, prestigious award for congratulations. Yeah. Yeah.
My name is Ian. I'm from State Department of ITB. So we all know that the oleh has applications such as for and so on. So, but the scientific process is not fully understood, and it's very complex and complex also. Yet it has the potential to open the door to tailor materials for advanced applications in and separation. And the question is, what's your opinion of this problem and what methods can be
Sorry, the final point. Question point.
The question is what the approaches can be placed to face the many black box in the second chapter.
Yeah. So I hope we open up several black box, but the based on this assumption, we propose several processes, but the still mechanism is not clarified yet. So even if we can propose some scheme, but not enough to frame the elucidation, of course, still analysis and the modeling is important to understand the mechanism. And but the engineer sometimes need answer before understanding all mechanisms. This is engineering. But it is very important to go towards combining science and engineering. Science is still very important to understand the real mechanistic understanding. But also, this engineer should utilize this knowledge. And we hope we can make important listeners.
So maybe last question from the student. Okay, from the UI. Please speak louder.
So we're trying to have a very responsive on this side. It's with organized and so I'm just wondering, what do you think about this solution?
Moisture is still, we have no clear answer because we have not worked on many. So this is just, I will use the paper.
how do they categorize this?
Yeah, yeah, yeah.
Carbon and zeolite. And zeolite.
Yeah. Yeah, already industrially separation of methane from CO2 is very natural gas separation. And of course, great assumption, remember water in advance is a very complex. Of course, the cooling the system in the industrial large scale, you can cooling down. Reducing the temperature is another way to reduce vapor pressure. So depending on the process, there are several. Actually, we are working controlling defect control to make zeolite is limited access of some water vapor. But every time water vapor exists in the environment, hopefully we talk better. Yeah, I have no similar answer.
Thank you, Sensei. So I think because time is up, so we have a lot of information from Okubo Sensei today about the synthesis of zeolite and strategy in the future, how we can continue this knowledge. So we thank again Okubo Sensei for inspiring talk. So I would like to invite Grand Prix and Prof. Yuni to come forward to give Sensei a souvenir. Please. So Dr. Grand Prix was also in Professor Okubo's laboratory when he was in the PhD for 1 month. Yeah, 1 month. Yeah. So please, Dr. Grand Prix and Prof. Yuni, maybe you can give a souvenir to Sensei and the cameraman, please. Cameraman. We have 2 souvenirs. One is maybe gift for. Foto.
Tapi nggak bisa masuk.
Okay. And another souvenir will be given to Yuni. Please, Prof. Yuni. Be careful, Prof. Yuni.
Thank you.
Okay, thank you, thank you. And yes, and then the next is actually we will have a group photo outside. Yeah, thank you. Yeah, let's give applause again to Professor Okubo.
Two rooms.
No problem. 11:30. We can leave for a while and then